There we go. Perfect. Okay. Do you have the packet, the key? Hopefully you have your calculator. Do I have my calculator? Yes. Your periodic table. If you're on Zoom, put questions in the chat so I can see it because it's right in front of me. Oh wait, I was going to put my camera on so you can see my dumb face. There we go. Hi. Okay, there we go. All right, so we will start. Let's just do chapter 8 quickly. Okay. Because it's like easy points, no math. So you just have to be kind of smart. So let's just go over the basics. Let's just go over the basics, all right? IMF stands for what? Intermolecular forces. These are attractions between particles. So it's funny, you know, in the one Kahoot where I asked like, what's the most important part of this chapter? People said bonds. We actually never talk about bonds in this chapter, meaning we never break or make bonds. That was all in like Lewis structures and stuff. We actually care about the attractions between particles. Those aren't bonds. Those are just attractions, right? There are no bonds involved here. So let's just go over the general trend. As attractions between particles increase, so if you think about your particles, all right, I feel like if you just use your intuition, you can get most of the way there. The more attracted your particles are, how is your boiling point temperature going to change? If they're real attracted, yeah, it's going to increase. It's going to be harder to boil your junk. Also related to that is enthalpy of vaporization also increases. So this is not the boiling point temperature, but the energy to vaporize something. So to turn it into the liquid phase to the gas phase, the energy required to do that is going to increase again because of attractions. More attractions, harder to separate. All right, what other trends did we talk about? Boiling point. So boiling point temperature is like the most like prototypical thing you look at when trying to identify intermolecular forces, those two things. So other things we talked about was viscosity. So how slowly something flows. Again, if particles are all tightly attracted to one another, are they going to let their particle friends flow past one another? If they're all attracted? No. So something that's highly viscous, so flows slowly, is going to have a high IMF. So viscosity increases, right? Viscosity meaning flowing slowly. So things that are highly viscous, things like honey, if you think of honey, all right, flows really slowly because those particles are super attracted to one another. What else do we talk about? Surface tension. Just memorize this one. Also has to do with IMFs increases. What's the one that decreases? Is vapor pressure. Vapor pressure decreases. So I feel like it's a misconception what like folks think vapor pressure is. Vapor pressure, all right, if we have a container of some liquid, right, those liquid particles, those particles are attracted to one another in the liquid phase. If you stick your nose in there and give it a whiff, and it smells like something, that means that that liquid exerts a vapor pressure that some of the particles are actually in the gas phase above it, some of them. That's why water will evaporate eventually, right? Like if I, spilled some water on this table and left it there for a long time, it will eventually evaporate, it'll eventually go away. But did that water ever boil away? Did it ever reach 100 degrees Celsius? No. So it is possible for liquids to go to the gas phase without actually boiling. And that is due to vapor pressure. And so another way to think of it, things that exert really high vapor pressures is anything that smells real bad. Any solvent that smells real bad. So think about, mineral spirits. Think about acetone. Can't think of anything else. Any other solvents that you use in the garage? What? Brake cleaner, because that's xylenes. Yes, brake cleaner. All of those things smell real bad because they exert really high vapor pressures at room temperature. So if they exert a high vapor pressure, is there strong IMFs between particles or weak IMFs? Weak, yeah, because the particles, they are not hugging each other tightly, all right, in the liquid phase, they're letting their friends go off into the gas phase, right? Does that make sense? Okay, so the idea of vapor pressure also tells us why stuff boils. Stuff will boil when your vapor pressure equals your external pressure. On Earth, what is that? 1 atmosphere. So water will boil when its vapor pressure equals 1 atmosphere. And that temperature just so happens to be 100 degrees Celsius. Ethanol will boil when its vapor pressure equals 1 atmosphere. That just so happens to be at a different temperature and so forth. What do we use as coolant in cars? Do we? No, we don't use water. Yeah, like antifreeze, right? And it has a higher boiling point because it actually has more IMFs than water. Because it's vapor pressure, it takes a lot of energy to increase its vapor pressure, really strong IMFs. It prevents it from boiling. That's why we can, get those liquids above 100 degrees Celsius and then not boil away. All right, so what is antifreeze? It's like ethylene glycol. Ethylene glycol looks like has carbons and junk on it. F2, so it looks like this. And then I think there's a bunch of hydrogens on it versus water, right? So the idea here, the difference between ethylene glycol and water has an unusually high boiling point because it has London dispersion, dipole-dipole, and hydrogen bond. But if you look at ethylene glycol, it actually also can hydrogen bond as well, and it's heavier. So that's why antifreeze or whatever, ethylene glycol has a higher boiling point. That's why we put it in our vehicles to cool them down so they don't boil away. Cool. So that's basically chapter 8 in a nutshell. If you can identify what intermolecular forces are present in your sample and you can apply these ideas of attractions, then you'll be fine. So let's do the hard part, and that's identifying IMFs present in things. So this first question, for each of the following pairs, determine which substance has the higher normal boiling point. So what is this question asking in terms of IMFs? Which one has higher IMFs? All of these questions basically are asking the same thing. So let's look at this. Let's look at A. If we look at these molecules, they both contain carbons, hydrogens, and nitrogens. Weird. Let's see where they differ. The first one only has 1 nitrogen. The other one has 2. What do we know about nitrogen when it's bonded to stuff? It usually has 1 lone pair. What's special about that lone pair? So there's ammonia. What's special about that molecule? Ammonia. So water can hydrogen bond. Can ammonia hydrogen bond? What's the criteria for hydrogen bonding? You need a very electropositive hydrogen. So essentially that hydrogen needs to be attached to something really electronegative, such as oxygen, nitrogen, or fluorine. It cannot just be any hydrogen. It has to be a hydrogen attached to a very electronegative atom, such as nitrogen. So can these hydrogens hydrogen bond? Yes, they can. So how I differentiate A and B is that A has 1 place it can hydrogen bond. This one has 2. So which one do you think has more IMFs? The second one, so that one's going to have the higher boiling point. So the trick to this one is that you needed to know that hydrogen attached to that nitrogen is able to hydrogen bond. That's the key here to this one. If you didn't know that, then you'd probably be lost and it'd just be 50-50. I could change this question, right? And I could change that nitrogen to be an oxygen. Would the answer change at all if I change it to oxygen? No, it wouldn't, because those hydrogens, again, still hydrogen bond. All right, what about B? Which one has the higher boiling point? BR2 or ICL? Which one? BR2. Why? Does it have a greater mass? You don't know? You just said it? Okay, BR2 is something like 80 times 2. ICL is 127 plus 36. What? Yeah, so they're actually basically the same weight. So we can't differentiate on weight. What else can we differentiate on? Okay, dipole, yes. Let's talk about all of the intermolecular forces. There's London dispersion, there's dipole, and there's hydrogen bonding. London dispersion forces usually are only important when things are all nonpolar, because it's the weakest. So of those two we just looked at, only one of them is nonpolar, and that's bromine. That's bromine. So ICL, because it's two different atoms bonded to one another, there has to be a dipole present. So ICL actually has dipole. And again, dipole is present in polar compounds. All right, so that one's going to like overcome, whatever London dispersion force there is. And then hydrogen bonding, the last one, a special case when you have that really electropositive hydrogen. All right, so the answer now to this one, BR2 or ICL? It is ICL because it is polar. So that means it has dipole in addition to the London dispersion that's there. All right, the last one, PH3 or SH3? SASH3. You might have to draw it. Do you remember how to do that? 6 steps, guys. 6 steps. P has 5 electrons, valence electrons. H has 1. So there's a total 3 coming from hydrogen. So we can place 8 electrons. So you put the P, you put the H's. Do I have other electrons to place? Yes. Where did they go? P. Good. Am I done? Yes. Now we do the same for ASH3. So we draw that one as well. AS has 5 electrons, and then there's 3 hydrogens, so plus 3. So that also has 8 electrons. What do you think it's going to look like? The exact same, yes. So AS, 3 bonds to hydrogen and a lone pair. All right. Which one do you think has the higher boiling point? So remember, there's only 3. There's only 3. London dispersion, dipole, or hydrogen bonding. So if you look at these molecules, are they polar or non-polar? Polar, yes, because they're trigonal pyramidal. So they're both polar. That sucks. So we can't differentiate on that. But what can we differentiate on? Molar mass. Yes. So the higher, so what does that mean about boiling point? The one that's heavier is going to have the higher boiling point, since they're both polar. So we can't differentiate on that one. So we'll just move to the next factor, which is London dispersion. Neither of them can hydrogen bond, so we can just ignore that one. So in this one, we can differentiate on mass on their London dispersion, because nothing else, it's really obvious where they differ on. All right. Do you think you can do that on an exam? Okay, all right. So of these substances, which exerts a higher vapor pressure at room temperature? So what is this question asking? Yes, lowest IMF. Okay, CCl4 and CBr4, what do you think? Chlorine or bromine? Yay, why? Lighter, yes, because both of them are nonpolar. Okay, the next one, the first one or the second one? The first one, all carbons. The second one, all carbons with the chlorine smashed on the end. It is the first one. Yes, because the first one is non-polar. The second one is polar. Water or H2S. Remember what we're looking at. We want the one with lower IMFs. This one can be tricky. Yeah, you said H2S, but H2S is heavier. It's a lot heavier, right? Why'd you say H2S? Or are you rescinding? Hydrogen bonding, yes. Water is weird. Water is weird because it's so light, yet it's a liquid at room temperature, has really strong IMFs because of hydrogen bonding. And I'm thankful for that because I'm a human being that lives on Earth and that water is wet or liquid. Okay, all right. Which substance based on their normal boiling points will be the most volatile? So volatile means highest vapor pressure. Volatile means smelliest at room temperature. So this is a little bit different. I'm not just straight up asking like, you know, which has more IMFs. I'm kind of asking it a different way. So how can boiling point temperature, how can we relate that to vapor pressure? If we relate it to IMFs, we can make that relationship, right? So look at these boiling points. Boiling point temperature trends with IMFs. How? If IMF increases, boiling point temperature also increases, but vapor pressure decreases. Yes. So what are we looking for? If we want the highest vapor pressure, most volatile substances, we want the lowest vapor pressure. Yeah, so it's going, or sorry, lowest boiling point. So what's the answer? B. B. So basically what this means, look, the boiling point of B is 18 degrees Celsius. So that means this thing, B, boils at like room temperature. It's like almost already a gas at room temperature. That's going to be the most volatile. It's going to smell the worst. Okay, let's keep going. All right, based on their vapor pressures at room temperature, so all of these vapor pressures are measured at room temperature, which will have the highest boiling point temperature? C. Yes, it is C. How'd you get that? It is the exact same thing. So the idea here is at room temperature, C exerts the least amount of vapor pressure. I like to think the least number of particles are in the gas phase. So you're gonna have to heat up C a lot to get it up to 760. Or you can think this, P vape, as that increases, IMF decreases, but boiling point also decreases. So we want highest boiling point. So we want highest IMF, lowest vapor pressure. So same thing. Good. Feeling better? Good. Feel like you're good when there's no substances, when there's no Lewis structures, then you're good. Okay. All right. Okay. All right. This one's tricky. Which substance will exert the highest vapor pressure at their respective normal boiling points that are given? Water, ethanol, or what is that? Ethane. Which will exert the highest vapor pressure at their respective normal boiling points. Yeah, D? Oh yeah, I couldn't trick you. It is D. It is D. What's the trick here? What's the trick? What did I try to trick you with? Yes, yeah, so anything will boil when its vapor pressure equals 1 atm. Normal, that's what normal means. Normal means on Earth. So that means these are the temperatures that this is true. So all of these will have vapor pressures of 760 torr at their boiling points. So that was a small thing. So see how in like the previous question, I gave these vapor pressures all at the same temperature, and these ones, the different temperatures are given because these are the temperatures these specific substances exert 1 atm. Yeah, that's why pressure cookers work, which I think is cool. Like my old school one, you literally put a weight on it to make the external pressure higher. So it's harder to boil water. So you can boil water at like 100, I think it's 103 degrees Celsius, which is significant. I think it's like 200, what's the boiling point of water in Fahrenheit? 212. I think it becomes like I think it becomes like 220 or something like a lot higher. And so you can boil stuff at a higher temperature in a pressure cooker. Or when you cook junk in Denver, right? When they have high altitude cooking directions, it's literally because their water doesn't boil at 100 degrees because there's just not enough particles in the air, not enough vapor or not enough atmospheric pressure there. Okay. If you went to a elevator shaft and went all the way down to like a cave, like a coal mining cave, and you try to boil water there, all the way in the earth, like a mile down, would the boiling point of water be 100 degrees, above 100 degrees, or lower than 100 degrees? Lower. Wait, lower? If you took a mine shaft a mile down, is there more, less, or the same amount of atmosphere particles above you? More. So is it easier or harder to boil water? Harder. So the boiling point temperature should be more. Yeah, you're literally like pushing on it. Yeah, you're pushing on it. Cool. I like that stuff. Okay, let's keep going. What statement about viscosity is false? Viscosity increases as temperature decreases. Remember, viscosity is flowing slow. So does junk flow slower when it's cold? What? Yes, it does. Yes.
Didn't we say something in class today that like got colder at less viscosity?
Today?
No, because we were talking about
Supercritical hydrogen or helium, that does weird stuff. What gets colder when it was in the notes? I don't remember. No, I would think as when things get colder, there's less kinetic energy. So the attractions between particles are going to take over. So they won't flow past one another as fast. When I make maple syrup, it's really hard to filter the syrup when it's cold. You always do it when it's hot. So it goes like straight through the filter. Okay, so A is true. B, viscosity increases as molecular weight increases. Yes, because viscosity trends with IMFs. IMF increases, viscosity increases. Viscosity increases as intermolecular forces decrease. No, that one's false, but let's just go through all of them. So I think C is the answer. Viscosity is the resistance to flow. Heck yeah. A highly viscous substance flows slowly. Yes. Cool. Good. That's chapter 8. Any questions about chapter 8? No calculations. Okay. All right. Let's do delta H. Stop being selfish. If you feel something get hot, the reaction lost heat and you gained it. You are the surroundings. Okay. So if you feel a cup and a reaction's happening and gets hot, the reaction loses heat. That is exothermic. It's a negative sign. I don't know how else to say it. Just remember all of those times we've done the hydrogen balloon, that's a highly exothermic reaction. All combustion reactions that we love to see are also exothermic, have negative energy signs because the reaction is losing that energy. And we as the surroundings, we're seeing that energy being emitted into the surroundings. And that's why we love it so much. Yeah. Okay. So just because you are gaining that heat doesn't mean Q is positive. It's the reaction that's losing heat. Okay. So let's assign signs. A system absorbs heat. So Q is heat, work is W. So what is the sign of Q if a system absorbs heat? Not you, the reaction. Yes, it is positive. Okay. What if your system expands against an external pressure? What is the sign of work? Remember, the system. So think about like a piston. And so think about the reaction, the little combustion reaction inside the piston. If the piston moves up, expands against an external pressure, is work being done on the system, or is the system doing work? Doing work. So this is a negative sign of work. Or just memorize this equation. Work equals negative P delta V. So expand. Delta V is a positive number, and because it's negative P delta V, work of your system. And again, we only care about the system here. System. Delta V is positive when it expands, so work of the system is negative. Versus here, if the system contracts, I like to think, okay, work of your system, if it contracts, literally me, the surroundings, I'm pushing on like my gas sample, making it smaller. I'm doing work on that gas system. So that is a positive sign of work when it contracts. Or you can think, put in this, shove it in this equation, all right? Contract, negative delta V. So it's a positive work of your system. All right, what is this? System loses heat. So Q is what? Negative. Okay. A system is endothermic. What's Q? Positive, yes. And contracts due to external pressure. What's the sign of work? Positive, yes. So it's the same there. A system is exothermic. Q is negative, expands against an external pressure. Work is negative. Do I give you the P thing? No, I don't. No, I don't. Okay, cool. So I don't think we answered this whole question. It says which process will always have a positive value of delta E? But I do give you that equation. So I calculated Q and work here. How is delta E related to that? It's just the sum. Okay, so delta E of your system, the change in internal energy of your system, is Q of your system plus work of your system. So which one will always have a positive value of delta E? C, a reaction that's endothermic and contracts due to external pressure. That one will always have, you're always putting energy into the entire system to make it absorb heat, absorb energy, and also contract. So that this one will always have a positive delta E because of delta E equals Q plus W. Cool. So an example of this would be you heat something up, but it shrinks. That would be an example of something. Okay. All right, let's keep going. All right, let's consider this exothermic reaction between hydrogen and chlorine. Did I have to tell you that this was exothermic? Nope, because I gave you a delta H of a reaction with a negative sign. So let's calculate the delta H of this reaction. How do you do that? Look at what's given and look how you manipulated it. So in the given reaction, I have 2 moles of HCl as my product. But if you look at my target reaction, HCl is not a product, it's a reactant. So how can I turn the first reaction into the second? I need to do what? I need to flip it, flip the reaction, make all of the products reactants and vice versa. But what else? It's not in the right number. So I need to also do divide by 2. Yes, because we have a 2 coefficient and a 1 coefficient there. All right, so then how do I manipulate the delta H of reaction? Do the same thing. So delta H of the reaction is equal to positive 186 over 2, whatever that is, kilojoules. So whatever I do to the reaction, I have to do to delta H as well. So if I multiply a reaction by 3, I have to multiply that delta H value by 3. Good? Okay, let's do another one. All right, same reaction. Let's calculate the amount of heat released when 25 grams of HCl is produced by this reaction. So this is just stoichiometry. All right. So I'm giving you how many grams of HCl I make. If this was a chapter 4 question, I could say, oh, go from grams of HCl to grams of Cl2, right? And you would just do the 2-to-1 ratio, molar mass, blah. But we don't want that. We actually want HCl to delta H of reaction. But the rules are the same here. 2 moles of HCl is equal to negative 186 kilojoules. That negative sign just implies that energy is being released. It just tells us the direction. All right. So in our answer, we don't need the negative sign within there again, because it just tells us direction. All right. So that's the stoichiometry we're going to use. Okay. So we haven't done this in a while. So 25 grams of HCl. Can I just go ahead and use that stoichiometry there? No. What do I got to do? Molar mass. Do you remember how to do that? Yeah, vaguely. I even give you the molar mass because I'm nice about that. But let's remind ourselves how to use molar mass. I'll just copy this conversion factor down here. So we're going to use that. All right. So I give you the molar mass of HCl. What this means is that 36.46 grams of HCl equals 1 mole of HCl. So when I do the next step, is the 36 going to go on the top or the bottom? Bottom, yeah. So 36.46 grams of HCl, 1 mole of HCl. Okay. What am I going to multiply by next? This is where I use the stoichiometry. Yeah. So where am I going to put that 2? Bottom, yay. 2 moles of HCl. And then the negative 186 kilojoules. But again, we don't really need the negative sign. It just implies heat is being released here. All right. And then we get some answer. Where's my key? I hope it's right. What number are we on? 9, 8. B 60, 63.8. I don't know. 63.8, whatever. Yeah.
Also use like the reaction, not the first reaction you gave us, but
The second one? Do you want to try it?
okay.
Okay, yeah, let's try it. Yeah, let's try it. So the question is, can we use the second reaction? Yeah, since we actually know the enthalpy of that reaction, it shouldn't matter. It shouldn't matter. So let me actually get this delta H of the reaction. I think the answer is something like 92 or 93 or whatever. My key says, I'll just say 92. My key says 93, right? So what's the relationship? That 1 mole of HCl, 1 mole of HCl equals 92 kilojoules. So we did the step where we did the mole conversion. Now we do the stoichiometry. Okay, so 1 mole of HCl is going to go on the bottom, 92 kilojoules up top. Do you get the same answer? You sure do. You sure do. Yes, so it doesn't matter. Whatever, doesn't matter. Okay. Okay, good. Stoichiometry, enthalpy. All right, let's write the thermochemical equation that represents the standard enthalpy of formation of iron 3 chloride. So I could give you a table. Yeah.
For number 8, it said released, and then you had a negative in your, like the negative 186.
Oh yeah. Again.
So would that be?
Yes, you could put it there, but again, how I'm phrasing it is energy's released. So I really should say 63.8 kilojoules released. If I say negative 63.8 kilojoules, like that's kind of weird. So we're just talking about magnitude. The sign tells us the direction. Because if I did this and like this reaction was endothermic, I would say 63.8 kilojoules absorbed. Yeah, that's where the signs get funky. But in a thermochemical equation, the sign is absolutely 100% required and tells you the direction. It's just how the language is kind of written here. It's kind of harder. Yeah. Okay. All right, so let's keep going. All right. So anytime you look up I like give you a formation value, like remember all those tables? Is there one with tables? Like here, all right? So here's like a bunch of table values, right? Formations of iron oxide, carbon monoxide, CO2. All of these formation values, they actually have chemical equations that relate to them. That all of these enthalpy values are specific to a chemical equation. So we have to remember what that chemical equation is. So that's our formation reaction. So a formation reaction is we take the substance that we're focusing on, and that's our product. And we want to ask ourselves, what elements do I need to form that? And then that formation value that's given is the enthalpy of that reaction. So we should be able to write, so negative 826 kilojoules. We should be able to write any formation reaction and understand what it means. So we ask ourselves, what elements do I need to make that? We want to choose elements in their most stable state. So iron, what's iron in its most stable state? Just a solid, yep. What about chlorine? Don't think about it too hard. It's Cl2 as a gas. Yes, so it's Cl2 gas. Is that balanced? No. So what is the coefficient in front of chlorine? 3? It's actually 3 halves. What we don't want to do, we don't want to put a 3 and then do like a 2 and a 2, because now this is no longer a formation reaction. The goal is we want to make 1 mole of this thing. So coefficients are absolutely okay. So we actually just want to leave it 3 halves. If this was like a, calculate the delta H of a reaction, and I didn't give you delta H's of, we actually already know the delta H's of formations of these things. Do you know what they are? They're 0. So essentially we're starting at 0, making our thing, and then that's what this number represents. How much energy is either released or absorbed when you make these things from elements in their 0 formation state. So substances that have 0 delta H's formation are any elements in their most stable state already. So oxygen, iron, any metal as a solid, nitrogen gas, chlorine gas, neon, those things all have 0. While all other compounds have non-zero formation values. And then they're nice because then we can like do the products minus reactants thing. That's why we're allowed to do it. Okay. All right. So let's do more delta H's. And I can like guarantee, if you haven't noticed, there's like one learning objective is every question. And that's basically how I write exams. Because this question, given these delta H values, calculate another reaction. That's Hess's law. That's a big learning objective. But here's the thing. I give you 2 delta H reactions, but I didn't give you the target reaction. I tell you what it is. So how do I get that? We have to write it. But didn't we already just write it? So here, calculate the value of the delta H of formation of iron 3 chloride. Didn't we just write it? Yes, we did. All right. So I saved us a step. This reaction we just wrote, this is our target reaction. So see how number 10 actually has like 2 questions kind of embedded in it, right? This one's tricky because I don't straight up just give you the reaction. You have to get it and understand what a formation reaction is. Okay. I like Hess's law questions because it's like a puzzle. All right. So these are our 2 reactions we get to play with. And we think, okay, how can we flip these, manipulate these to get what we want? So I focus on like one substance at a time. So if you look at iron here, iron shows up in that first reaction. We need it in our target reaction. Do I need to do anything to that first reaction? Nope, I don't. But what about the second reaction? So focus on a substance that matches the target reaction. So for example, here, I would, for neither of these reactions, would I focus on chlorine, because chlorine shows up in both the first and second reaction. So I don't want to try to like take this chlorine and multiply by 3/2 because I'm just gonna screw it up with the second one. Does that make sense? So basically what we wanna do, focus on substances that only show up once in each reaction given, and pray that the rest cancel out to get what you want. And that's what we're gonna do. We're just gonna pray that chlorine cancels out to 3/2, right? So iron is in the right place, but then if we look at iron chloride, is it in the right place? No, we need to do what? Flip it, so times -1. Is it in the right number? No, so we need to divide by 2 as well, because there's only a 1 coefficient there and there's a 2 there. And so we can add up the new delta H reactions. So we're gonna just leave that first one as is. So 341.8, and we're gonna subtract 115.4 divided by 2. So just add up those two numbers. All right, and we should be able to get our real reaction. But I want to prove it to you that these two reactions, if I do that manipulation, we get the target reaction. So I flipped the second one and I divided by 2. So I'm going to just rewrite that up here. So flipped and divided by 2. So iron Cl2 plus half a chlorine, arrow, iron 3 chloride. Okay. So I'm adding these two reactions, these two. So just ignore that one. Okay. Think about how things cancel. All right. So I'm left with an iron. That's what I want in my target reaction. I'm left with an iron chloride. That's what I want in my target reaction. What about this iron 2 chloride? I don't want that in my target reaction. But what's special about it? It gets canceled. See how it shows up? I'm adding this first reaction to the second one. I've tried to line up the arrows, but I did a poor job. So you can see that iron 2 chloride actually cancels. It falls out when you add those two up. And then when you see what's left, how many chlorines are those? 3/2. Is that what we want? Yes, it is. So they do in fact add up to what we want. And so the praying we did to get chlorines, yeah, it happened. Okay, all right. So then there's the answer or whatever. Yeah.
You use the same numbers for 9 and 10.
Yeah, I
The
tried that.
9 is the -826, but this is not.
Oh, it's not. What's my key? Oh yeah, my key says -8, -399.5 kilojoules. Yeah, that's just my mistake. This number doesn't matter, right? Yeah, sorry. Good, because this is what happened. When I was writing this, I copied this from 1210. I had you write the formation of iron oxide, and I think this is the delta H of iron oxide. But then I looked at the next question. I'm like, wait, but I'm already having you do a formation of iron chloride. So I just changed it, but I didn't change the number. Sorry.
I mean, the fake number.
Yeah, they are fake numbers. Okay. Yeah, I could put any numbers here and you couldn't tell. Good. All right, perfect. All right, let's do calorimetry. Let's say we have a block of aluminum and a block of copper. They're your specific heats. True or false? Aluminum has a larger specific heat than copper. What do we think? True. Cool. The heat capacity of a 5-gram aluminum is greater than the heat capacity of a 10-gram of copper. How is this question different? Specific heat, we just compared the 0.88 to 0.39. Oh yeah, I see some calculators coming out, love it. So heat capacity, you have to embed the mass in there. So I'm asking you, how much heat do these specific, these unique objects absorb? So if I multiply 5 grams by 0.88, I will get the heat capacity of that aluminum block. If I do 10 grams times the copper thing, I'll do it for copper. So I think for copper, it's 3.9 joule Kelvin. I think I can do that math. And then for aluminum, what is it? 4.4. joule Kelvin. So the heat capacity of a 5 gram aluminum is greater than the heat capacity of 5 grams of copper. True or false? True. Yes. Good. 10 grams of copper is more resistant to change in temperature than 5 grams of aluminum. What did we just calculate? We just calculated heat capacity. What does that mean? It means if I wanted to heat that, this is specific, this unique 5 gram block of copper, I would have to deliver 3.9 joules to raise it 1 degree. Aluminum, this unique block of aluminum, I have to deliver 4.4 joules to get it to raise 1 degree Celsius. So go back to C. The copper is more resistant to change than aluminum. True or false? False. Okay. 10 grams of copper can deliver more heat to a small cup of water than 5 grams of aluminum. No, it's false. Is that what you said? Oh, I thought you said yes. It's false. Yes. Yes, because the heat capacity of copper is smaller. All right. 1 gram of aluminum will deliver more heat to a cup of water than 1 gram of copper. True. Yes. What thing did you look at? The specific heat. Yeah, because they're for a per gram thing. And so that's what we are looking at there. So that one's true. 1 gram of aluminum is more resistant to change in temperature than 1 gram of copper. True. Yes. Okay. So the big difference here is that like these middle ones had to do with heat capacity, which embeds the specific heat and the mass, right? So in some of the questions, and I showed a lot of these in like the Kahoot and like practice exams, oftentimes I do like, 10 grams of aluminum, 10 grams of copper, 10 grams of gold or something, and I give you the specific heats. If they're all 10 grams, I can literally just ignore the mass and just look at the specific heat. But what if they're not the same mass? Then you compare heat capacities. That's it. And so you just multiply the mass amount, and that will tell you the heat capacity. Good? Okay. All right. Oh, our favorite. Do you like these questions, these calorimeter questions? No, they're literally, okay, here's the deal. This question can take a long time. It can take a long time. But if you get the process down, it's actually a really quick question because there's only one way I can ask it. And it's always the same junk. Some gram amount of salt in some gram amount of water. The water either goes up or down in temperature, and I give you the molar mass. And I ask you to calculate delta H. It's asked the same every single time. So if you can get the strategy down, great. If not, take the L and just skip it on the exam. Because this question, if you don't know how to do it, it will eat your time. And I don't want it to do that. Right? So, but there is one question we can answer right away. Is this reaction endo or exothermic? Is delta H, should it be a positive or a negative number when you're done? You should be able to tell without calculating anything. It should be negative. Why? Because the temperature, yes, it went up. The temperature of the water increases. Yes. So delta H is negative. So we should be able to glean that. All right. So this is the way I do it. I just know that negative Q of your reaction equals positive Q of the solution. And that is in your thingy, kind of. I wrote negative Q lost equals Q gained. I said negative system equals Q surroundings. That's the first law of thermodynamics. Heat lost somewhere is gained somewhere else. The heat of the reaction is being gained by the solution itself. So the solution is equal to the mass of the solution, the specific heat of the solution, times the change in temperature of the solution. We are given all of that information in the words that are given here. What's the mass of the solution? What's the mass of everything in the cup that's being increased in temperature? 126. You guys are so good. Yes, it is not 120. That's a mistake that students will make all the time. They just think, oh, it's the water that's increasing in temperature. No, it is everything that you threw in that cup, including the water, including the 6 grams of junk. All of it increases in temperature. All right, specific heat of the solution. We're assuming it's water. So 4.184 joule gram Kelvin. Now delta T. So that one is, it's always T final at minus T initial. So since the temperature is increasing, this is a positive delta T. Did I write it down? No, I didn't. Can someone do that? Thanks. Positive 8.6 degrees Celsius. The temperature went up. All right, so that's delta T, 8.6 degrees Celsius. All right, do all that math. Can someone give me that number?
537,
Wait, what? 30?
45, 37.71.
Okay, that's fine. Joules. Joules. Did we get that too? Yeah, we got that. Okay. All right. So what we're saying is that the solution, the cup, everything in that cup, it went up some amount of, temperature, and that equated to 4.5 kilojoules of heat. That's how much energy it took to raise the temperature and everything in that cup, 8.6 degrees. Is that our answer? No, that's just Q. Also, see how we just calculated a positive number because it requires energy to heat the solution, but we care about the reaction. So Q reaction is actually negative 4537.7 joules, right? That's still not our answer. We actually want delta H of our reaction, which is equal to Q of our reaction over the number of moles of junk you actually reacted. And that is in here. All right, so this is the last step, where we just divide the heat amount we just got and we divide by how many moles of stuff we actually reacted. So I'm just going to take that Q amount. I'm going to quickly convert it to kilojoules. So 4.5377 kilojoules. And I'm going to divide it by moles of calcium chloride. So do I divide by 6.23? No, that's grams. So I need to take that gram amount, incorporate the molar mass. Oh, it's right there. All right. So 6.23 grams of calcium chloride divided by 110.98 grams, 1 mole. And then that's our answer. So for me, this is a quick calculation. If you know what you're doing, to combine the masses, that this everything in the cup, right? The mass of everything in the cup, the solution has the same specific heat as water. You get delta T, check your sign. Because when we get, does someone have the, oh, I have it in front of me. What is it? Negative, what number are we on, 12? Yes, negative 81 kilojoules. That's what I got. Hopefully you got that too. Okay, negative 81 kilojoules. So does that answer, that delta H, does that match our observations of what happened? Negative 81 kilojoules. Does that match? This delta H implies the reaction is exothermic, right? Is that what our observations called for? Yes, the temperature went up. Okay, so use your intuition, because if you get this question, if you did all the work right, but you still did this question wrong, you know what you forgot? The sign. And the story I tell is that I took this 1210 exam, right? We do this, we teach this in 1210. I took this exam, it's their midterm 2. I took that exam in 7 minutes. It's 30 questions, I took it in 7 minutes. I got one question wrong, and it was this one. And you know what I messed up? The sign. It was the sign. I got the number right, but it was the sign was wrong. I was really mad. I don't try to take it really fast anymore because I don't want to disappoint myself. Okay. All right. Who's doing this question on the exam first try? Or you guys skip it? Is everyone skipping it? Skip and come back. Very good. Very good. But you can predict the sign just like that, right? Okay. So if it's multiple choice, you can eliminate half of them, right? And if it's a multiple choice question, what are the distractor questions I'll put? I'll put the answer where you forget mass of the salt. I'll have the answer where you put 120 in here. I'll have the answer where you don't do this last step. Yes, okay. Using standard enthalpies of formation. Calculate the delta H of these reactions. What's the hint here? I don't give you the equation, but what is it? Products minus reactants. So these are your formation values. So we can just use the products minus reactants and the appropriate stoichiometry. What you're actually doing is Hess's law, FYI. So just be really careful of the stuff. So iron, I like to take inventory of things. So iron is negative 826. Yeah, 826. See, that's the number. Yeah. Kilojoules, CO, and remember, there's 3 of them. So 3 times 1, negative 110. 3 CO2, so 3 times negative 394. Well, where's iron? Did I not give you enough information? No. What's the formation of iron? 0. Yes. So this is what I like to do because there's tons of negative signs. And I get so mad when you guys are doing the Kahoot and you don't have a calculator. And then students, they're using their phones. And then they're like, how do I put a negative sign in a calculator? And I'm like, I thought you guys take competition seriously. Who was in the Thursday Kahoot today? You guys? Yeah. Thursday didn't do so well. Yeah. I know you won, but the team that won in Thursday wouldn't have even placed like top 3 on Tuesday.
Listen, you do as good as you have to do.
Yeah.
That's
You don't want
true.
to be first place.
That's true. Should I post it in the recap, the results?
Yeah, team on.
I like how you guys are uplifting. You don't bring each other down. Okay, this is how I do it. What? I do. I know. I like to pit you guys against each other. So you do better.
You know Thursdays.
What? The Thursday group? I don't know about that. I always do feel bad for the Tuesday group because they're oftentimes doing a lab like I haven't taught yet. And I'm like, wow, they get the short end of the stick. Yeah. But the Thursday group, I have my review sessions on Thursday. So you guys, Thursday, they've been doing chem since 11:10. Okay. So what I do is I take inventory of everything, add up the sides separately, then do the subtraction, and I'm less likely to make a mistake. So 3 times negative 394, that is negative 1182, and then the other side, negative 826, minus 3 times 110 is negative 1156. And so then I do products minus reactants, negative 1182 minus negative 1156. And then whatever that answer is, I don't know. Negative 26 kilojoules. I don't know. Sure. Okay. Next one. Same idea. So you know how to do that, right? Products minus reactants. Keep track of the negative signs. Don't screw up. Okay. Don't try to do it all in one line. You don't have to be a superhero. It's not like you're trying to save money, save like bits on your calculator. Don't try to do it in one. I do it all separately so I don't screw up. Okay. All right. Let's keep going. All right. Ooh, chapter 10. All right. Enthalpy. Delta H is energy. Energy. First law of thermodynamics says what? Aren't you all in physics? You don't remember? Energy's conserved. Energy's conserved. If something loses energy, something else gains that same amount of energy. All right? Yeah? Like the calories that you eat. Right? The calories that you eat, the amount of energy, right, via calories that you eat should equal the energy that you use, right? That all of that energy is conserved. Okay, that's the first law of thermodynamics. Does the second law of thermodynamics say entropy is conserved? No, it doesn't. Correct. Yeah. One might think that. You might think, oh, like if the first law says energy is conserved, second law says entropy is conserved. It's not. The second law of thermodynamics says that reactions are spontaneous if the delta S, the entropy change of the universe, is positive. It's completely different. Entropy is not conserved. So oftentimes when we're studying the universe, what does the universe constitute? The system and the surroundings. So we oftentimes have to keep track of both of those. So as long as the sum of these two things are total positive, any reaction is spontaneous. Any process is spontaneous. Okay, so true or false? A combustion reaction will always be exothermic and have a positive delta H of reaction. True or false? What's an exothermic reaction? Why do we love them? Yeah. So is this true or false? Why is it false? I didn't say anything about spontaneous.
That's not.
It is false, but why? Yeah, the second half. Yeah, you saw the positive delta H. Does that mean exothermic? No. Exothermic always means negative delta H of reaction. Always, always. Q is always negative. Always. So I made it. So in order to make this right, I would put the negative right there. It is true that combustion reactions are always exothermic. Yeah. But it was the last bit that was wrong. Okay. A decomposition reaction will always have a positive entropy change of the reaction. Do I need to remind you what a decomposition is? Yes. Okay. A gives you B and C. True or false?
True.
Why?
You have more moles.
More moles. You went from one thing to two things. Entropy increased, microstates increased. Statistically, where you can put two things, there's way more places and combinations you can move around two things than just one particle. Okay, all right. The second law of thermo says that delta S of your reaction is positive, your reaction is spontaneous. True or false? No, you're all false. You're all wrong. It's false. I literally wrote it right there. I wrote it right here. It's not delta S of the system. It's delta S of the universe. Yes. 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 Okay. So that one's false. So this really should say universe. You read what you want to read. Yeah. Okay, you can't do that on conceptual exams. I'm very deliberate. You can't just be like, I think Dr. N meant this. Then you just change the question. Okay? No, you should read it how I intended it to be written. So. Okay, all right. If delta S of your reaction is negative, the reaction can still be spontaneous if delta S of your surroundings is very positive. Yeah? Why? You just felt like saying that?
Yeah.
Okay. No, yeah, read this that I wrote up here, right here. Delta S of the universe. The second law says when that is positive, the reaction spontaneous. Universe is system and surroundings. So if I said system is negative, I said the reaction can still be positive if surroundings is very positive. Oh, yeah. You see it? Yes. So that one's true. Cool. If delta S of your surroundings is very positive, then the reaction is very exothermic. There's an equation in here that helps you. I'll just write it. delta S of your surroundings equals negative delta H of your reaction over temperature? Now answer it. That negative sign is there. It's not a mistake. This is true. Okay. If a reaction's exothermic, what's the sign of delta H? Negative. So if I take a negative of a negative, you get positive. Yes. Here's another way to think of it. Okay. An exothermic reaction, does it absorb heat or release heat? Exothermic. Don't think about it. Release. Yes. So if combustion reaction, right, releases heat, shouldn't the surroundings get hotter? When you combust something, right? The surroundings get hotter. What did we say about entropy with a function of temperature? Hot stuff has more entropy. So here, an exothermic reaction releases heat. It's going to add more entropy to the surroundings because it's releasing that heat. But that's what this equation says as well. It says the same thing. But I want you to think about it conceptually. I want you to get to that point where you can do that and not rely on an equation. But the equation helps us when we're feeling down on ourselves. Okay. When the forward and reverse reactions occur, the system is at equilibrium. Delta G equals 0. Yeah? Heck yeah. Yeah, it is true. Why? We were just talking about positive universe, right? Spontaneous reactions, but spontaneous in one direction. So that means if a reaction is both spontaneous in the forward and the reverse, right? That the delta S of your universe isn't positive, it's actually not changing at 0. So delta G is also 0, right? You're at equilibrium. What?
I thought you said in the lecture that delta G could never actually be 0. You just said equal 0 for like solving.
Did I say that? You don't remember. See, I don't trust you that much. No, I don't trust you.
I just remember.
No, I said S. I said S cannot be 0.
I thought it was when we were solving for like H and S and you said it equal to 0 because that's when it's like the change.
Yes, that the idea here is when delta G is negative, you have a spontaneous reaction. When delta G is positive, it's non-spontaneous. So a lot of times questions will ask, okay, when is a reaction not spontaneous anymore? So we're kind of looking for the inflection point here. So we just set delta G equal to 0 to figure out, okay, where does that separation happen?
I thought we were explaining it before you said it.
Couldn't equal, no, it can equal 0. It'll be at non-standard conditions. That's the idea. Yeah. So, yeah, I don't know. I said for a fact, S, entropy of junk can't be 0. Maybe you're mixing up that because we learned about a lot of letters. Okay. Yeah. Okay. All right. Okay. Yeah. Speaking of entropy, let's order in order of increasing entropy. So what are our factors? Phase, temperature, complexity, molar mass. So A, what has the most entropy? The second one. Yes. Why? It looks the biggest. Yes. It's the heaviest. It also has the most bonds. So I like to think, okay, these are all gases, right? So we can't just think about like gas, liquid, solid. We have to think past that. So we look at complexity. So I like to think the more bonds in your gas particle that are there, gas particles that have a lot of bonds, they bounce in your gas phase, but they also wiggle. And if you can wiggle, that's a lot of entropy. If you can bounce and wiggle. Can krypton bounce in a gas container? But can it wiggle? No, it can't wiggle. Which one can wiggle more? This one or HCl? This one, yeah, because HCl can only do this. It can't wiggle. Well, I mean, I guess it's like wiggling a little bit. It's just stretching. Yeah, so if it can wiggle a lot while it's bouncing, it has a lot of entropy. And that's why complexity matters in terms of entropy. If you looked up the entropy values of these, you'll see that HCl4, it has the most. Which one has the least? Yeah, it'll have the least. Yep. All right. All right, what about B? Which one has the most entropy? The gas, yeah. These are all the same substance, they're just different phases. So this one's the most, then the solid is the least. So we don't have to look at complexity or anything, we're just straight up looking at phases. Okay, C. Which one has the least amount of entropy? The liquid, yes. Least. Which one has the most amount of entropy? Br2. There's two of them. And if there's two things bonded, they can wiggle. Yeah. What? It can kind of wiggle. It can stretch. Also, you might think, oh, well, what about molar mass? Molar mass, maybe molar mass. Oh yeah, bromine is also a lot heavier. It's also a lot heavier. So for two reasons. Okay, good. Now you will remember the wiggle thing. Okay, so hopefully that will get you one question right. Okay, let's predict the sign of entropy in the following reaction. So it's the same question. We're just looking, okay, which side of the reaction has more entropy? To predict what is the change, what is the sign of change. Actually, this should say change in entropy because this is a reaction. So just, small detail there. Okay, because in these examples, we were actually just calculating the absolute entropy of these things. So not delta S, just S. But in 16, we are looking at the change in entropy. So A, is entropy increasing or decreasing? It is going down. Why? Less moles, yeah. You're going from junk that's dissolved into junk that is just sitting at the bottom of your chest tube. Okay, so if you think disorder, that's fine. That's fine. Okay, sodium carbonate to sodium oxide and CO2. Delta S, the change in entropy of this process is positive, yes, because we're going from no gas to one gas. All right, the last one. H2 and an oxygen give us water. Water in the liquid phase. Yes, decrease. For a couple reasons, you're going from 3 to 2 and you're going from gases to liquids. Good. All right. I'm going to skip that one. I want to do, no, we can do this one. The enthalpy of vaporization of mercury is that while the molar entropy of vaporization is that. So that is delta S of the reaction is 92.9 joule mole Kelvin. Calculate the boiling point temperature of mercury in Celsius. So what equation has delta H and delta S in it? On your equation sheet. The delta G one. Delta G equals delta H minus T delta S. Okay, so it looks like we have delta H, we have delta S, we want T, but where do we get G? Did I just not give you that table value? No, we want to set that equal to 0. So the reason why, if I write the actual equation, chemical equation that's happening, we're taking mercury, so Hg liquid, and what are we doing? We're vaporizing it. Hg solid. So I don't, so I could be thinking, okay, yeah, I want this reaction to be spontaneous. I want to calculate when delta G is negative, when this goes forward, what temperature that happens. Or I can just figure out, okay, if I set delta G equal to 0, I can figure out when this equation first becomes negative to be spontaneous. So that's why I'm setting it equal to 0. I want to figure out when does this first become spontaneous? Boil it, no, not solid. I boil my mercury like that, turning it from a liquid to a gas. All right, and so we just plug in the number, set it equal to 0, be super sure of your units because enthalpy is given in kilojoules per mole. Entropy is given in joules. So you need to convert one of them. Which one do you want to convert? H or S? Just pick one. I don't care. Some H. Okay, so I want to convert H to what unit? Joules. Yeah, so you're not going to put 59.11 in the equation. You're going to put 59.11 times 10 to the 3 joules per mole. Yeah. Okay. So that's what I do. I set that equal to 0, the delta H value. So 59.11 times 10 to the 3 joules per mole, minus T delta S. So 92.9 joule mole Kelvin. So, or you could have changed delta S to kilojoules. Don't matter. Don't matter. And now when you calculate it, you're going to get a much more reasonable number for temperature. This was the most missed question on the Kahoot, when I just had you estimate the boiling point of methanol. Yeah, and the reason was because you just didn't convert. You what?
We didn't even use math, we just logicked it.
Oh, for 60, it was like 65 degrees. Yeah, everyone put like 0 degrees Celsius. It was like 0 point. So if you do it without converting it, you got like 0.3 degrees Celsius. And you said you're saying the boiling point of methanol is freezing. Come on. Come on. I know. It's okay. It's okay. All right. And then you solve for that. Temperature is what? Something. 636. What's the unit? That comes out when you solve for T. Kelvin, but you know I'm not going to ask for Kelvin on the exam. I'm asked for Celsius. So then you subtract 273. And so the answer you actually report is 636 degrees Celsius. Right? Okay, good. Okay. All right, let's do another one. Do you like math or concepts?
Concepts. Yeah, concepts.
You can do this one? You can do this one? Will you get the units right?
Well, I didn't say I like
Okay.
concepts.
You didn't say you were good at it. Okay. So without doing any calculations or looking anything up, look at this combustion reaction and choose the correct statement. This reaction is spontaneous at high temperatures, low temperatures. It's never spontaneous. It's always spontaneous. Yeah, it depends on a lot of things. Yeah. I actually give you all of the information you need. How do we determine if something's spontaneous or not? Delta G. And what's the equation? Delta G equals delta H minus T delta S. Great. When is a reaction spontaneous? When delta G is negative. Well, that doesn't help me. I don't know delta H or delta S, or do I? You do, because I tell you what kind of reaction is this. Also, you should be able to tell what kind of reaction this is. Yeah, it's combustion. So what's the sign of delta H? It's gotta be negative. I like your confidence. You're right, though. It has to be negative. Delta H has to be negative. Well, how do I get delta S? You look at it. And it is what sign? Positive. So when is this reaction spontaneous? Based upon the signs. So change in your mind, change temperature. What I do is I write it like this, and I literally change the size of delta S. I go like this, I go like this. If temperature is big, is delta G still negative? Oh yeah. What about if it's really small? It's still negative. So what does that mean? It's always, yes, it is always spontaneous. So D. Okay, let's, for fun, let's say it was negative, let's just say we did another reaction and entropy was negative. So same idea, because this is what trips up students. It's what is the temperature range, right? So when T is really big, what's the sign of delta G? Positive, yeah, because you're subtracting a really negative number. Okay, well, what about if T is really small? What's the sign of delta G? Negative. So in your mind, literally just like blow up that delta S term, whether it be positive or I don't know. That's how, in my mind, that's how I do it. But I have a very vivid imagination. Good. Is that what I said? I hope I said that. Yes, will always be negative. Wait, D? Yes. Okay, cool. All right. Thermite. Make sure you charge your calculators for Monday.
Yeah.
Okay. Do you have that like stupid fat USB thing for it? I have one of those in my office.
It's not the full, so it's like mini USB.
Is it mint? Is
They're
it?
mini, it's not
No,
the
no,
micro.
no.
It's fat.
Is it the
It's
fat
like-
boy?
No, it's not as big as that one. No.
Oh, not this one?
Oh, wait.
No,
It is. It is that one.
It's the fat boy.
Yeah.
It's like not the ones that like Samsung users use.
Yeah.
It's fatter than that.
Yeah.
Yeah. I sound like a guy.
Stop shaming me, stop wanting to shame me calculators. They don't-
No, I was shaming. There was like, I saw a comedian. He's like, there's no more discriminated group in the world than Android users. And I was like, that's
That's so
true.
true.
That's true. That's true. It was funny because he was like, you know, don't judge me on the content of my blog, but you judge me on the color of my texts. It was very well, there's a very good canter to it. Yeah, and I felt it. Okay, so let's keep going. Be nice to everybody, even if they have dumb Androids. Sorry if you have an Android. No one? No one? Nice. All right. Okay, so thermite reactions used for welding. Cool. So there it is. You take iron oxide, you add aluminum, you make aluminum oxide and iron. So let's calculate delta H and delta S for this reaction. So what do we do? What do we do? Yeah, products minus reactants. That's it. But we gotta do it twice. We gotta do it for delta H and then we gotta do it for S. So we can just ignore the delta G's for now. So I'm gonna just kind of try to do this quickly. So products, so iron and aluminum oxide. So pink is my products and then yellow is my reactants. So delta H equals my product. So negative 166, 9.8 plus 2 irons. But look, even in this chart, it says iron solid has a formation of 0. You see that in the table? And it has a delta G of 0. But iron solid does not have an entropy of 0. Nothing can have an entropy of 0. So do note that. Okay, so minus all of the reactants. So iron oxide, so negative 822.16, nothing from aluminum. So there's some number. Then we do delta S. So same thing, but do make sure you know, everything has an entropy now. So aluminum oxide, so 51 plus 2 times 27.15. I like entropies because they're always positive numbers. I get scared of negative numbers. All right, and then the reactants. So 89.96 plus 2 times 28.32. All right, so you get that. You get the numbers. So delta H is some number and it has a unit of kilojoules. So negative 847.6 kilojoules. That's delta H. And then delta S, what is in what unit? Is it also in kilojoules? No, sir. It is in joules. You can tell from the table. See how it says it right there? Yes. So delta S is, okay, negative 41.3 joule Kelvin. Cool. All right. Let's keep going. All right, let's assume delta H and delta S do not change with temperature. Decide whether thermite can be used to weld railways in Antarctica, where the average temperature is negative 57 degrees. I don't know what temperature that is. 216 Kelvin. So how can we decide? How can we decide whether this reaction can be used in Antarctica? Delta G, yeah. So delta G equals delta H minus T delta S. So if I plug in all these numbers, I know delta H, I know delta S, and I was given a temperature. So if I plug all of those in and the sign of delta G is negative, can this reaction be used in Antarctica? Yes, because the reaction is spontaneous. But if you plug all those numbers in and delta G is positive, can this reaction be used in Antarctica? No, because the reaction is not spontaneous. So you just plug everything in. So, but do make sure the units match. Okay, so I'll just do negative 847 kilojoules minus T. So 216 Kelvin times that entropy number. So negative 0.0413 kilojoule per Kelvin. All right, and then you get some number. I got B. Yeah, that you just get a negative number. I didn't actually calculate it. So just you get a negative number. Yes, delta G is negative, which means this reaction is still spontaneous at 216 Kelvin. So again, assuming delta H and delta S do not change with temperature, let's decide, is there a temperature that this reaction is no longer spontaneous? How would I figure that out? Set it equal to 0, right? Because right now we know that, at room temperature or at 216, it's a negative delta G. So if I just figure out when delta G turns 0, that tells me the cusp where it becomes positive again. So yeah, you just do the same thing, but you set it equal to 0. So 0 equals negative 870.47 minus T, now we're solving for T, times negative 0.0413 kilojoules Kelvin. And again, make sure your units match. And you get a crazy temperature. It's like 20523 Kelvin. So a crazy high temperature is required for this reaction to not be spontaneous anymore. So above that temperature. So like in the pits of hell, the thermite reaction will not happen anymore. Okay. So the whole like delta G equals delta H minus T delta S, it can get us out of a lot of pickles when we set it equal to 0 or predicting spontaneity. And personally, I like the delta G reaction gives free energy more than entropy of the universe. Because I don't like to keep track of the system and surroundings. But it's cool to predict that, yeah, you put an ice cube in your hand and it melts because entropy of the universe is changing. And I think that's pretty cool, but yeah. Okay. All right, 30 minutes. Can we do kinetics? How did we think this chapter was? Kinetics? And remember, homework is due on Monday. You're gonna be tested on it. Okay. Okay. Yeah. Hopefully it's not too bad. I don't know. So it is like the weird one in this chapter. I feel like the last two absolutely relate to one another. Not so much this one. All right. The reaction in a breathalyzer to determine the alcohol level in someone's bloodstream is below. If the rate of appearance of that is 1.24 moles per minute, what's the rate of disappearance of that? So it's just identifying, what am I pointing at? So it looks like C2H6O, that's ethanol. So that's right here. That's a reactant. And then the other thing, chromium sulfate, is right here. And so really it's just stoichiometry. So I'm giving you the rate of appearance of the chromium sulfate thing. So 1.24 moles of the chromium sulfate thing is appearing per minute. So how am I going to set up the stoichiometry to get to ethanol? Where am I going to put the 2? Where am I going to put the 3? 2 on the bottom. Yes. So 2, 3, there's your answer. So it's 1.86. I don't know. I think that's right. That's it. Stoichiometry. Okay. All right. So given K equals that for reaction, what is the initial rate of the reaction in meters per second, molarity per second, when the initial concentration of A is that? So that's A, initial, so A0. So what is this? Rate stuff, right? Rate stuff. So I give you rate constant. I'm asking for initial rate. I tell you the concentration of A. What's my order? Do you know? Can you tell? Can you not tell? First, how do you know it's first? K, yeah, the unit of K, it's second to the -1. So if it's first order, can't you write a rate law for it? Rate equals K times A. That's it. That's it. Because it's first order. If you would have told me, oh, it's second order, then we would just do that. So from the unit of K, you were able to get the order. So at this point, it's just plug and chug. I give you K. It's 6.2 times 10 to the -3, second to the -1. Then I put in A, so 0.0050 molarity. Also, when you multiply those two things together, what's the unit that comes out? Molarity per second. And that's exactly what we want. And so that has an answer. And it's in the key. So just multiply those two together. So the idea here is if I would have said, oh, okay, K is that number, but it's molarity to the -1 second to the -1. How would this question change? If I just change the unit of K right there, what does that imply? It's a different rate law, but what is it? If it's molarity to the -1 second to the -1. Second order, yeah, it's a second order, and you can tell. So by when you plug in the numbers, so it wouldn't be K A to the 1, it would be A squared, and then you would do that. You would propagate it that way. And so the unit here, -1, when you would put all of this together with the appropriate unit, you will get the appropriate unit of rate out, molarity per second. It all works out. Nothing is arbitrary. Yes. Okay, good. So I didn't tell you it was first order because I'm evil. Okay. All right, let's look at this reaction, which is first order with respect to A and 0 order with respect to B. If the overall reaction rate is blah, when A is blah and B is blah, what is the reaction rate when A is new stuff and B is new stuff? So what should I start with? This is just like a Kahoot question, but in the Kahoot, I laddered it. I would only start with the first question and I would say, what is the rate law? So why don't we just take the first sentence and decide what is the rate law? So from what I highlighted, rate equals K times A. B, 0. So that means B is just 1, it falls out. So this is the rate law. A, that's it. Boop. That's the rate law. Okay. So now I'm saying if the rate of the reaction is that, when A is that and B is that, what is the new rate? So the idea here is the first piece of information, all of this, I can shove that into the rate law and I can calculate K, can I? And then I can take that K and then plug it into the next part. Yeah, so that's what I'm going to do. So the first part, that what's highlighted, I'm just going to say 0.525 molarity per second equals K times 0.100 molarity. That's A. So note how I just ignored B because it's not in the rate law. But if it was, I would just include it. All right. And so we get that K, I can do this math. 5.25. And then the unit would be second to the -1. Okay, and that's not my answer. I want to use that answer again for the new condition. So it says, what is the new rate when A is 0.25? And so I'll just take that K, 5.25, second to the -1, and then multiply by that new. So 0.250 molarity, right? And then that's my new rate. It should be faster. Or you could think about it this way. You could just say, oh, okay, A is 0.1. The new A is 0.25, so it's increasing 2.5 fold. And if it's first order, then your rate should increase 2.5 fold. That's another way to do it. You can just think your way out, or you can just do the math. Just do the math. Just do the math. Good? Do we like kinetics? No. Okay. All right. The consumption of donuts by Homer Simpson follows zero order kinetics. If the rate constant for this 0th order process is 5.0 donuts per minute, how many donuts will be left after 4 hours if Homer starts with 1,024 donuts? Okay, 0th order. So which rate law do we use? Yeah, the regular concentration one, the first one. If you look on the thing, 0th is in fact first, then it's first, and then it's second, but it's read left to right. So we're going to use this one. A to the T equals A to the 0 minus K. Is it minus KT? Yes. Okay. Do we know everything? We probably do. So yeah, we're using 0th. What is this 5.0 donuts per minute? What is that? That's the rate constant. That's K. Yes. How many donuts will be left? What are we solving for? A sub T. 4 hours is T, but there's a problem. It doesn't match K. So I'm going to just quick change that to minutes. So that's that many minutes, 240. Okay, good. So I want to put 240 in the integrated, not 4 hours. And then what is 1800? What's that number? What? Initial, yeah. And then it's just plug and chug. Good. We should get a donut number that's less than 1800 at some time later. So, so equals 1825 minus 5 donuts per minute times 240 minutes. I don't know what the answer is. 625 donuts. This episode, I wrote this question, the episode where Homer's in hell and then they feed him donuts in this like donut machine. And it's just like a constant flow of donuts and he just keeps eating them. And then like a while later, you see like the devil, like it pans away, comes back. The devil's like waiting back there and there's like no more donuts. What? Yeah, they did. Yeah. And I think by looking at the rate of consumption of Homer, I'm pretty sure it was first order kinetics. It was just a constant rate of just like donut, but it was actually, he was eating 2 donuts at a time. Yeah, and so it was actually a lot more than 5 donuts per minute. Absolutely. So. Okay. Do you like mechanisms? I like mechanisms. I think they're fun. Because the whole idea with mechanisms is that what? The slow step is the rate determining step. Here's the thing. I I showed a lot of pictures of dudes building bikes in the slides, but I never explained why. It's like an analogy, like the steps it takes to make a bike, right? There's like multiple steps to make a bike, right? Okay. And so if you had different teams building your bike, the rate at which you produce end product bikes depends on your slowest team member. You ever work in a group and see how you're held back by the slowest person, right? So it's the same idea. If it takes a really long time to put on the tires, your total output is going to depend on that person making the tires. It's not going to depend on the person who slaps the bow on at the last minute, right? It doesn't matter. Like that bow can come on, off. That's a fast equilibrium step because slapping a bow on doesn't take any time. It's really fast. But taking the time to like tune the spokes, or I don't know how to build a bike, all those things, those like intricate steps, that's your slow step. That is what's going to dictate the overall outcome of the bikes that you make. Okay, so based upon this mechanism, okay, it's 2 steps. 1, 2. Which step is your rate determining step? Step 2. Yeah. So with mechanisms and with elementary steps, it is now absolutely okay to just take the reactants and then put them in your rate law with the appropriate coefficients, only when it's mechanisms. When we did, like the integrated stuff, when we did initial rates, we use experimental data, but with mechanisms, it's okay to just put reactants into our rate law. So does that mean that rate equals K times NO3 times NO? Are we done? Are we done? Is that my rate? Yeah, you might think like, yeah, it is, but what's the problem? What's the problem here? Our rate law can only have what in them? They can only have reactants. So there's a problem. Am I allowed to have NO3 in there? No, I'm not. I can't have that. So I need to get rid of it. So I'm going to use step 1 to get rid of it. Right? So this intermediate is not allowed. It's not allowed to be in there. And we're going to get rid of it using the fast equilibrium step. So we just learned about equilibrium, right? The forward rate is equal to the reverse rate. So I can write the rate law for the forward reaction for step 1. I'll just write it down here. So this is for step 1. K1 times NO times O2. Oh, wait, no, yeah. Times O2 equals K -1 times NO3. And so by using this equilibrium step, I can rearrange this, isolate NO3 so it's in terms of all reactants, and then plug it back into my initial rate law. And that's how I get rid of it. So I see that NO3 is equal to K1 over K -1 times NO times O2. And so now I can shove that back into the rate law. But I'm just going to call K, like I'm just going to combine all these Ks and just call it K. So this is actually K2, K1 over K -1. Let's just call it K. So when I replace all of this in with that intermediate, I think this just becomes NO squared O2. So I think our answer is A. Our answer is A. So this one's harder. Let's pretend, do I have another one where it's a slow step? No. Let's pretend we did this mechanism, this 2-step mechanism. Let's pretend that the first step was slow and the second step was fast. What would the rate law be if the first step was slow? It would just be first order to NO, first order to O2. That would be it. That's it. And then you'd be done. I recognize it is harder when the slow step is the second step, where you have to get rid of an intermediate, but it's not bad. I trust you. You can do it. No, just remember, you can't have an intermediate. That's it. So you just use the fast steps to get rid of it. I just set I just set the forward reaction equal to the reverse reaction and rearrange things to get the intermediate in terms of just reactants. It's not,
That question pretty much has to be multiple choice, right?
yeah, it has to be. Yeah, I can't have you type it in.
That's fine.
Then it's fine. It's fine then? I mean, but look, okay?
Multiple guesses.
So you might think it was this one, right? If you, like, you might say, oh, it's D, right? The intermediate thing, yeah. Okay, all right, okay. All right, same mechanism. NO is a what? NO3 is a what? So again, two-step mechanism, 1, 2. NO is a what? Look at it with your eyes. Yes, it is, because it's in the first step and it's in the balanced equation. Okay, NO3 is we already said it, is an intermediate. Why? Because it's produced and in the first reaction and it's consumed in the second reaction. It doesn't show up in the balanced chemical equation. What would a catalyst look like? A catalyst would look like this, where it shows up as a reactant, but then it's produced as a product at the end. So it gets canceled for the balanced chemical reaction. That would be a catalyst. So see how like the cat is like this? It's this way. It's like that. But then a intermediate is like that. Okay. And then neither show up in the balanced equation. They're all like behind the scenes. All right, let's do 2 more. I think we can do it and then we'll be done. Do you like talking about catalytic converters? I learned a lot about catalytic converters and why it's important not to run lean or rich. Got to be right in the middle so you get effective electron transfer. Oh, yeah. If you take off the cat.
Or just run really rich.
Yeah, let's not do that. Yeah, because then you're sending uncombusted hydrocarbons into the atmosphere and it causes birth defects. Do you want that?
Well, that's why they think something.
I'm sure.
When
When I was teaching 1210 last year, I had an engineer. I talked about catalysts and like tractors and stuff, and he got really excited. People like to talk to me about cars. I don't know a lot about cars. And he came up to me and he was bragging to me that he took the catalyst off of his I think it was like a Subaru. I don't know. Some crap. Oh, the Subaru. Yeah. And he took it out because he wanted it to be louder. That's it. He just wanted it to be louder. He said it was restricting his airflow.
That's why you get performance cats.
Yeah.
But or
Test pipe.
yeah, but like actual performance cats have less.
Is anyone not mechanical right now? Is in here? Do you not like cars?
Actually,
They're cool, but I don't spend my time.
Okay.
Yeah, they have larger money.
I'd rather talk about cars than bodies.
Which is insane.
Yeah, but
Bodies.
test pipes-
Yeah, they're gross.
Bodies are boring.
Yeah, they're gross. Okay, 8 minutes. Let's do the last 2. Look at this data. Look at this data. What is the rate law for this reaction? How do we get it? What? The tricks, yes. Where we look at 2 reactions, 2 sets of reactions where one reactant stays the same and the other one changes. So I'm going to look at 2 and 3, reactions 2 and 3. So NO stays constant, O2 doubles. What happens to the rate? Double. So what does that mean about O2? First order, yes. So then we got O2. So now let's do NO. So what experiments are we looking at? 1 and 2. Wow, I made this super easy, didn't I? Okay. O2 stays constant. So now all changes in rate are coming from NO. So NO is increasing 2-fold. So how is the rate increasing? Does that, I think that's 4. Sure. So that means what is the order of NO? second. Cool. So the rate law is rate equals NO. Oh, I forgot the K. Forgot the K. K NO squared O2 to the 1. Cool. Yes, tricks. I love tricks. Yes. Okay, calculate the rate constant with proper units. How do I do that? How do I do that? Plug it in. Which one? 2? Do I have to do 2? You can do any. Yes, you can do anything. And you should actually for fun, okay? Just once. Just once. Just once. Do it for all of them. And just see that you get the same K. Just see it. Not for this one. I'm just saying sometime in your studies. Not on the test. Not on the test. Do it just on your practice exams and prove to yourself you can plug in any experiment and you should get the same K as long as your rate law is correct. Okay. All right. So yeah, we just plug in. Which one are we doing? Number 2, because you guys are creative. I told Matt that I wish I could put a time limit on you guys picking names for the Kahoot, because that took so long.
I already got my name ready for the next one.
Good, good.
I wasn't allowed to do mine.
The what?
I'm the surrounding.
You are the, yes, yes, yes.
Ours got like changed on me. Yeah. I changed it.
Oh, well, someone,
It was
oh, it did?
academic weapon.
You put weapon?
The word weapon, not.
Oh. I don't know. What did it change it to?
Griffin, Smiley Griffin 17.
1 second.
Someone tried to write MCAT, Q equals MCAT, but it got auto corrected to meet.
Oh, yeah.
All right. Yeah. Okay. We'll plug in number 2. So rate 5.64 molarity per second equals K times NO. So 0.0252 molarity squared times 0.0125 molarity. All right. So what is the unit of K? It's to the negative square. Yeah, S -1. Good. That's the unit. And then whatever that answer is, you guys can get it. Good. Just plug in something. Okay. Calculate the rate when that equals that. What do we do? Oh, so I should probably get K. What is K? K is 7.1 times 10 to the 3. So how do we get the rate? Plug it in. You just plug it in. Now we actually have the full rate law. So rate equals K, we just got it, 7.1 times 10 to the 3, molarity to the -2, second to the -1, that's K, times NO concentration, we're given it now, 0.0750 molarity, but that needs to be squared, times O2, 0.01 molarity. That's it. And then the rate is 0.400. So it's just, you plug it in. But this C, it's contingent. We can plug it in because we know what K is. We know what K is. Yeah. And remember, to get K, we get it from the experiments. Okay. All right. Okay, last one. Activation energy for a reaction is 95 kilojoules per mole. The rate constant at 25 degrees Celsius, so that is equal to 298 Kelvin, is 0.15 molarity per second. So what, do you know what order reaction this is? It's 0. If that's the unit of the rate constant, you don't have to know, that's fine. For this question, you don't have to know it. So there is the temperature. And so I'm telling you that the rate constant at this temperature is 0.15. And now, so I'm asking you, estimate the rate constant. So K2 at this new temperature, 75 degrees Celsius. I don't know what that is. 75 plus 273 is 348. So that's T2. So what equation do I use? Point to it on the piece of paper. Whereabouts is it? It's like on the middle bottom. Yeah, that one. Because this reaction, we don't want to use the one in the right corner, right? That one has activation energy in it, but it doesn't have two temperatures. We want to use the middle one because it has two temperatures, two rate constants, so we can clearly associate activation energy. It's basically the 2-point form of the Arrhenius equation. So you just plug and chug, but this equation, it's ln K1 over K2 equals EA over R, T2 to the -1 minus T1 to the -1. So where are you going to screw up here? You're either going to screw up K1 over K2, T2 minus T1, or you'll screw up right here, the unit of activation energy. What does the unit of activation energy need to be? What's the unit of R? Energy, joules. Yeah, so R is 8.314 joule mole Kelvin. So that means activation energy needs to be in the unit of joules as well. But I give it to you in kilojoules. So you don't want to put 95 in there. You want to put 95 times 10 to the 3, or you'll be sad. You'll get a weird number. All right, so let's plug everything in. So ln K1, so 0.15 over X, that's what I'm solving for, equals 95 times 10 to the 3 over 8.314 times T2. So 348 to the -1 minus 298 to the -1. This is how I do it, okay? I will do all of that math. And I will get ln equals 0.15, or sorry, no, ln 0.15 over X equals all of that garbage. 95 E3 divided by 8.314 times 348 to the -1 minus 298 to the -1. So I get all of that is equal to -5.509. How can I isolate X? You E both sides. Yes, very good. You guys aren't good at physics, but you're good at math. Okay, so when I E both sides, what does the left side become? Yes, point. Yeah. 1/5 over X. Yeah. Equals that junk. Equals. I'm gonna put you over here. 0.004049. And so then you just move some stuff around. So I'm gonna do 0.15 divided by that number. And so I get X equals 37 molarity per second. 37. Yeah, very good. But wait, does that make sense for this answer? Sure? No. We heated up this reaction. The reaction should go faster. So the K we got is, yes. That's it. Okay, yay. All right, wow, we did it all. Okay, see you guys.
After I think we're going.